Hello everyone. Today, our group, which consists of me, Shun Wei, Ranishaa, and Hanisah, will be presenting the questions from our field theory assignment. The first question is about the magnetic field, and the second question is about electromotive force. Let us begin.
In question 1, it shows that a coil of 300 turns is wound uniformly over an air ring having a mean circumference of 400 mm and a uniform cross-sectional area of 500 mm square. If the current through the coil is 4 ampere, calculate the magnetic field strength, the magnetic flux density, and the total magnetic flux. Well, coiling a wire uniformly over an air ring will create a toroid. When current passes through the wire, the magnetic field will form inside the toroid. The magnetic field inside the toroid is composed of concentric circles. Magnetic field is a vector field in the area around a magnet, electric current, or changing electric field in which magnetic forces are observable. Here are some examples of magnetic field. We can use the magnetomotive force formula to calculate the magnetic field strength of the toroid, while the magnetic flux density can be calculated by using the following formula. The magnetic field strength or the magnetic flux density were both used to determine the intensity of the magnetic field. The unit for magnetic field strength is amperes per meter, while the unit for magnetic flux density is Newton meters per ampere, also known as Teslas. The magnetic flux can be found using the vector dot product. Magnetic flux is the measurement of the total magnetic field which passes through given area. In the case that the surface is perpendicular to the field, the angle is equal to 0.
Question 1a. To find the magnetic field strength. We are given in the questions that the number of turns N is equal to 300. Then the current I is 4 ampere and the circumference L is equal to 400 millimeter. We can substitute these values into the magnetomotive force formula and get the answer for magnetic field strength. It is equal to 3000 amperes per meter. B. The magnetic flux density. The permeability in free space is 4 pi times 10 to the power of negative 7. The magnetic field strength H is equal to 3000 ampere per meter as we calculated just now. It can be put into the magnetic flux density formula. Then we will get the answer for magnetic flux density as 3770 microtesla after rounding up. C. The total magnetic flux. The magnetic flux can be calculated by multiplying cross-sectional area with the magnetic flux density. Multiply the magnetic flux density we got from question 1b with the cross-sectional area 500 mm squared. We will get 1.885 Weber as the answer for total magnetic flux. Next, we will start the discussion for question 2.
Figure 1 below shows a wire and a metal rod. If the metal rod moves with constant velocity of 5 meters per second, find V12. Figure 1 shows a straight wire which has current flowing through it and also a metal rod. The direction of the magnetic field line for the straight wire that has current flowing through it can be found by using the right hand grip rule. Imagine your right hand gripping the wire with your thumb pointing in the direction of the current flowing. The orientation of your fingers that wrap around the wire shows the direction of the magnetic field. The magnetic flux density of a straight wire then can be calculated by applying the Ampere's law. Magnetic flux density is equal to the relative permeability of air times current divided by 2 pi radius. The magnetic flux of the straight wire will shift when you move the metal rod at a constant velocity. Any change in the magnetic flux will cause electromotive force to be induced. By applying the Faraday's law, the electromotive force induced can be calculated. Electromotive force is equal to velocity times with magnetic flux density times with length. The direction of the electromotive force or current induced can be found by using Fleming's right-hand rule. The thumb represents the direction of the movement of the metal rod. The forefinger represents the direction of the magnetic field, and the middle finger represents the direction of the induced electromotive force or current.
Solution to question 2. The value given in the question is stated at the right side. And then the magnetic flux density formula is given, as well as the electromotive force induced formula. The electromotive force induced formula, the length will be replaced by the integration from the shortest distance of metal rod to the current source, then to the furthest distance of the metal rod to the current source. Formula of magnetic flux density is then subbed into it. After rearranging the formula and putting the figures into it, we can get the electromotive force induced as 1.3863 times 10 to the power of negative 5 volt. This is the end of the video. Thank you.